October 30th, 1961, Novaya Zemlya archipelago, far north of Russia. On the surface, it looked like any other day, just another cold morning in the Arctic. But 10,500 meters above the ground, a Soviet Tupolev Tu-95 bomber was about to change history forever. In a moment that felt like something out of science fiction, humanity was seconds away from creating a second sun on Earth. Back during World War II, the Manhattan Project gave birth to the first nuclear weapon, based on fission, the splitting of atoms. But at the very same time, there were already whispers in scientific circles of a concept that went beyond that fusion, the same process that powers the sun. The idea? Use the explosive force of a fission bomb to ignite something far more powerful, a fusion reaction. And believe it or not, the concept was already on the table in 1941, 4 years before the first nuclear explosion had even happened. Back then, Edward Teller, the same man who helped propose the fusion bomb, spent much of his time in the Manhattan Project obsessed with making fusion a reality. But there was a problem. While fission could be tested, studied, and refined using early nuclear reactors and radioactive isotopes, fusion was a whole different beast. It was untouchable, unpredictable, and largely a mystery. Scientists had split the atom, but could they fuse one? And more importantly, could they weaponize it? While fission was known, measurable, and in some terrible way, manageable, fusion was what powered the stars. They were trying to bottle the sun, and on October 30th, 1961, they did. So far, we've been throwing around two words that are absolutely essential to understand the rest of this video: nuclear fission and nuclear fusion. And to make sure we're all on the same page, let's break down exactly what they mean and, more importantly, what makes them so different. When we talk about fission, we're usually starting with a heavy atom like uranium-235. This isotope is unstable and nature doesn't like instability, so what does it do? It splits. Uranium-235 breaks apart into smaller, lighter atoms, releasing energy in the process. But here's where the magic happens. The mass of the resulting atoms is less than the mass of the original uranium atom. And according to Einstein's equation, E=mc2, that missing mass doesn't just disappear, it transforms into energy, a lot of energy. That's why fission powers both nuclear bombs and nuclear reactors, because that lost mass becomes explosive force or usable electricity. Now fusion, that's the opposite. Instead of splitting heavy atoms, fusion involves taking light atoms like hydrogen and smashing them together to form something heavier like helium. And just like in fission, if you measure the mass before and after, surprise, surprise, the resulting helium has less mass than the original hydrogen atoms. Once again, that missing mass gets converted into pure energy. Fusion is what powers the sun. It's the engine behind every sunrise you've ever seen. So while fission splits atoms apart, fusion fuses them together. Fission is what we've mastered on Earth, what we use in nuclear plants and atomic bombs. Fusion, on the other hand, is what stars do naturally every second of their existence. And as we're about to see, learning how to force fusion on Earth is what made the hydrogen bomb possible. Just a quick note, when you hear thermonuclear bomb, hydrogen bomb or H-bomb, they're all names for the same thing. A weapon that uses nuclear fusion to unleash energy on an entirely different level. The biggest challenge in building a fusion bomb isn't the science, it's the conditions. To make atoms fuse, you need to rip them apart first, strip away their electrons until you're left with just their nuclei. At that point, they become what we call ions, but there's a problem. All nuclei carry a positive charge, and like charges repel, so to make them collide you need to overcome that natural repulsion, and that requires insane levels of heat and pressure. How insane? Well, the only reason the Sun can achieve fusion naturally is because it has 333,000 times the mass of Earth. Its gravitational force is unimaginably strong, squeezing atoms together until fusion happens constantly in its core. So here's the real engineering puzzle. How do we recreate that level of pressure and temperature on Earth? How do we as humans simulate the heart of a star inside a bomb? The breakthrough came from two physicists, Edward Teller and Stanislaw Ulam, who found an answer to the fusion bomb dilemma. And their idea? Well, blow up a regular atomic bomb first. All right, they didn't phrase it quite like that, but that's essentially the simplified concept behind what we now call the Teller-Ulam design. There's actually a bit of mystery here too. We still don't know exactly how much each of them contributed individually. Some historical accounts suggest Teller did more. Others lean toward Ulam. But due to the classified nature of the project, we'll probably never know the full truth. What we do know is that this design revolutionized thermonuclear weapons. In the Teller-Ulam model, the bomb is built in 2 or more stages. 2 is the minimum, but massive bombs like the Tsar Bomba likely had 3. The first stage, a standard nuclear fission bomb, just like the ones from the Manhattan Project. Its only job is to explode with enough energy to trigger the second stage, where fusion finally begins. Remember earlier when we said fusion requires extreme conditions like those in the core of the Sun, which has 333,000 times Earth's mass? Well, this first stage explosion creates just that kind of environment. When the fission bomb detonates, it generates temperatures reaching 100 million degrees. And at that level, it doesn't even matter whether we're talking Celsius, Fahrenheit, or Kelvin. The numbers are so high, the differences become irrelevant. This unimaginable burst of heat and pressure is what kickstarts the second stage, which contains fusion fuel, typically made from light atomic nuclei like lithium deuteride. The energy from the first explosion compresses and heats this fusion material to the point where nuclear fusion begins, releasing even more energy in a violent chain reaction. This is why the Teller-Ulam design is so brilliant. It uses the destructive force of one bomb to ignite an even more powerful second explosion. It's efficient, scalable, and terrifyingly effective. That's why it became the blueprint for almost every modern thermonuclear weapon in existence today. And this leads us directly to the first ever thermonuclear bomb test in human history. But just before we dive into that incredible moment, give me 20 seconds. Check this out, the shirt I'm wearing right now. It's part of the brand new collection from my store, Lose. If you like wearing smart, science-themed designs and want quality that lasts, we've got a deal. Click the link in the description or the pinned comment, grab your favorite tees and use the code LOOSE10 to get 10% off your first order. Because if you're into the kind of stuff we talk about on this channel, chances are you're going to want them all eventually. And Loose isn't just stylish, it ships fast, like relativistic speed fast. You buy it, we ship it, no delays. Alright, promo's over, back to the science. Let me tell you what really happened the day humanity first tested a fusion bomb. November 1st, 1952, a remote island in the middle of the Pacific Ocean, Enuitak Atoll, Marshall Islands. After successfully creating fission bombs during World War II, the world's next logical step was to build something even more powerful. With the Teller-Ulam design finally on the table, all that was missing now was a full-scale test. And that's where Ivy Mike comes in, the first hydrogen bomb ever detonated. But forget what you imagine when you hear the word bomb. Ivy Mike wasn't a bomb you could drop from a plane. It was more like a nuclear science experiment inside a building. Weighing a massive 74 tons, it used liquid deuterium as fuel, which had to be kept near absolute zero. Yeah, that cold. They literally had to invent cryogenic tech from scratch just to make this test happen. Still, despite all that, the test went forward, and what happened next was nothing short of apocalyptic. When Ivy Mike exploded, it was like opening a portal to another dimension. A fireball 5 kilometers wide tore through the sky, big enough to swallow an entire city. The iconic mushroom cloud, it soared 41 kilometers high. That's 4 times taller than Mount Everest. And it kept expanding until it was 161 kilometers wide. The explosion was so intense it created 2 brand new elements never seen before, Einsteinium and fermium. To put it into perspective, this one blast released 1,000 times more energy than the atomic bomb dropped on Hiroshima. This wasn't just a bigger boom, it was a whole new level of destruction, and that should have been a huge wake-up call. But in reality, it was just the beginning, because the world, caught in the middle of the Cold War, wasn't done proving its power, and the Soviets, they were about to one-up the planet. October 30th, 1961, Novaya Zemlya, far north of Russia. Just another cold, quiet day, until it wasn't. Flying at 10,500 meters, a Tupolev Tu-95 bomber was about to change history forever. Inside, the most powerful explosive device ever created by humans, the Tsar Bomba. Nicknamed the King of Bombs, it was based on the same fusion design tested with Ivy Mike, but taken to an absolutely insane scale. The original plan? 100 megatons of TNT equivalent energy? Let that sink in. That's 100 million tons of TNT, 100 times more powerful than the Hiroshima bomb. But even the Soviets thought that was pushing it, so they scaled it down. The version they dropped only released 50 megatons. Still, the fireball alone was 8 kilometers wide, reaching all the way up to the altitude of the bomber. And even though the plane had flown 39 kilometers away, the shockwave still hit it hard. Hard enough to throw the aircraft 1 kilometer downward mid-air. In fact, Soviet estimates gave the crew a 50-50 chance of survival. This photo shows the mushroom cloud from the blast. Looks small, right? Now consider this. The photo was taken from 161 kilometers away. The top of the cloud, it reached 67 kilometers into the sky, 7 times taller than Mount Everest. The shockwave from the blast didn't just echo through the region, it circled the entire Earth 3 times. The aftermath. The detonation of the Tsar Bomba left a scar in human history that we'll never forget. To this day, it remains the most powerful explosive device ever unleashed by humanity. But here's the twist. This symbol of ultimate destruction also marked the end of an era. Because once we built a weapon with destructive power so massive we used to compare it to gods, the world realized something terrifying. There's nowhere else to go from here. Shortly after, world leaders came together and signed the Partial Test Ban Treaty, agreeing to stop testing nuclear weapons like the hydrogen bomb in the Earth's atmosphere. It was a turning point, at least on paper, but there's something I find incredibly unsettling. Everything you've seen in this video, every blast, every mushroom cloud, every fireball the size of cities happened decades before most of us were even born, and that gives us this false sense of comfort. Like nuclear danger is a thing of the past, like all of this is just a dark chapter in some dusty history book, but that's where we're wrong, dead wrong. We're not living after the nuclear era, we're still right in the middle of it. The bombs may be quiet, but they haven't gone away. Thousands of them still exist, armed and waiting, part of a global balance we all silently hope holds firm. It's a delicate game of don't press the button. And that button, it's still very real. Every decision made by world leaders, every conflict, every tense negotiation, they all play out in the shadow of weapons that could literally end civilizations. And that's why it's so important to understand this stuff, because the more we know about how fusion bombs work and just how much damage they can do, the more we realize that this isn't just science, it's survival. And maybe, just maybe, one day if you or I ever find ourselves in a position of influence, we'll remember what this power really means. We'll do everything we can to make sure that humanity never again measures success in megatons. Thanks for watching, and I'll see you in the next one.